Welcome to the demo of our product TwinARC in a real-life setting. We have chosen a single asset, an industrial fryer of one of our customers who is one of the largest fryer manufacturers. Industrial fryers are the engines of fast food restaurants like McDonald's, KFC, and so on. They are the source of French fries, chicken strips, and hash browns. One type of operational assessment is about the quality and the dynamics of frying. Another is the operational value they want to derive from the asset. How are the fryers working? How reliable are the electrical and mechanical systems? Are there any issues or likely problems in the offing? Can we go in and perform proactive maintenance before something happens? And so on. The fryer in question is just one of a whole host of fryers, but we will select the state of Washington for our demonstration. If you click on this button here, you can see 2 fryers. While there are many more in the state, we are analyzing the data only for this one particular asset called an XY fryer at a local McDonald's in Tacoma. Once we click here, we get the digital twin interface. What we see here is something much more than a traditional dashboard with charts. The display is more intricate, comprehensive, and gives a broader view of the workings of the asset. We can see various buttons to select the fryer. Then within the fryer, select what date, what type of equipment, and even observe and evaluate real-time data. As the fryer is operational, you can see displays changing and going red, green, and blue accordingly. Operationally, what is immediately relevant is the data on what is overcooked, undercooked, and so on. As you observe, the current condition flashed up on the top row. In the middle row, you observe the day's stem plot. A normal indication means chicken has been cooked properly. Ideally, the chicken should be around 165 degrees Fahrenheit inside temperature. Overcooking and undercooking are a matter of concern. This information is being visible to the store manager. Is this something happening at other stores too? Can we compare? Yes, we can. This is one way the fryer maker can help improve the operations of their end customer, such as McDonald's. Compare to another store. Select the same model fryer in a different store. Right from this dashboard, we can see there are very few red and blue, indicating they are very well cooked. This could mean 2 things. It could be that the franchise at this store has trained the cook properly. He is waiting after one frying round for the oil temperature to come up to the right point before he puts in the new set of chicken strips, which means he's going by the book. But here, it is not so. Many over- and undercooked chickens, which means it could be either operational, that the cook was not trained properly, or there is a technical problem. It is possible that the control system for the temperature is not as sensitive or responsive as this other case. So a lot of useful information just from an operational point of view is derived instantly in real time. Now let's dig deeper. This is the traditional digital twin view. You get this high-level information, and for each different use case, a special UI like this overcooked, undercooked comparison will go straight to the fryer. Now you're actually seeing the endpoints or sensors or nodes. This is the oil level sensor. This one is the oil temperature sensor. Now here's the sensor for oil flow. And then we have the current or amperage or the electricity sensor. You can see details for each sensor in the dashboard that popped up on the left. If it is red and flashing, it indicates something is not right. The stats engine is saying it may not be that bad at a probability of 0.14, so it's a low probability event. With currently available simple digital twin algorithms, a lot of false positives show up all over the place. One should really look into much more robust measurements for higher levels of accuracy and deeper levels of prediction. For this, we have another tab. That is the Robust ML. This is a meta-learner for conducting other advanced machine learnings. Robust meta-learner does its work in the backend and shows that there is indeed failure. In fact, that number you saw earlier was misleading. There is a high probability of failure of 0.8, so this is something you should go and look at. The unique and exciting aspects of TwinARC will be demonstrated next. Causal graph simulation and optimization of performance. One could create and evaluate the causal graph. This is actually the fryer operating and how things are working in real time. The current temperature is running at over 200 degrees Fahrenheit, drawing over 30 amps. The oil level is like 6 inches, half a foot in that trough. Instead of just seeing these 4 sensor node values, what you're seeing is how they are connected, not just based on some thinking, but estimated using the data that we've been collecting from it continuously. It has estimated this causal graph and all the interconnections, and their strengths are shown. These are the causal directions and weights. Temperature is one of our main concerns, so when we click this button here, you can see all things that are connected to the temperature parameters and how they are connected to the other nodes. These are causal weights. These links are all active and affected by all 3 parameters. Now, this is where we can do things with TwinARC that cannot be done with any predictive model. Let us say we want to give a recommendation to the franchise to help them save costs. We can do an experiment in software to prove how we can reduce electricity consumption by 10%. That would be a huge saving over the year. But of course, we should not be changing the temperature while reducing power consumption, which is what the whole optimization algorithm can do within TwinARC. We can go and change the value here. The optimization algorithm has told us that when this causal weight becomes 0.8, we would achieve the required result of lower power and proper cooking temperature simultaneously. Let's click the sim button and initiate the simulation. You will notice that C is affecting T, and T is affecting other parameters. We have these rotating effects till they settle down. Now we have concluded the iterations and reached convergence. Now you can see we are almost 2 amps less, so it's about 10% less. You can also see the temperature is being maintained. Even if it is 220, we're still at a safe level for cooking chicken. So one can conduct this kind of analysis without having to go to the fryer and reduce current or run at various oil flows and so on. This will impede production, sales, and can be dangerous. What we have observed as the optimized solution is one kind of frying, shallow frying. This is the power of TwinARC beyond the visibility that traditional digital twins produce. Robust condition prediction, cause-effect relationships, simulation, and optimization of fryer operations. All with an intuitive, easy, and engaging UI/UX. Thank you for your time.